Now I would like to invite our next speaker, Taro Mieno. He's Associate Professor in Department of Agricultural Economics at the University of Nebraska-Lincoln. Welcome.
Okay. All right, so I have to tell you first that you'll get a very different feel from my presentation than the previous one. It's kind of dry. And that's what you get if you invite economists to talk. All right, so my topic is groundwater management, and there are regions in Nebraska and Kansas and elsewhere where some level of limit on how much groundwater should be pumped is needed, right? But there's a good way of doing it, and there's a bad way of doing it. Here what I'm going to talk about is how what would be a good smart way of doing that regulation of groundwater pumping. All right. So I don't have efficient groundwater management is critical, right, for sustainable, profitable agricultural production in Nebraska and in elsewhere, Kansas, Colorado. Okay, and quota, which is the limit on groundwater extraction, is the most common form of groundwater use regulations in Nebraska and Kansas, but its design varies significantly across NRDs and GMDs. Okay, and I haven't seen any systematic evaluation of the economic and hydrologic implications of how the quota system is designed. Okay, and that's what my presentation is going to be about. Okay, so here are some examples of existing quota designs. Okay, so there are four important kind of parameters in quota design. So one of them is allocation length in year. So for example, if you look at Lower Elkhorn, it has 1 year. That means, with annual quota of 8 to 15 inches, typically 13 to 14 inches. So that means you will get farmers are given the right to pump 13 inches annually, and you will be given that quota every single year. Okay, but if you go to tri-basin, allocation length is 3 years, and annual quota is 9 inches. That means you will be given 27 inches at the beginning of an allocation period, and you can use 27. You can allocate that 27 inches within the 3-year period, unlike getting 13, 14 inches every year in Lower Elkhorn. Okay, imagine you're a kid and you're getting an allowance of, let's say, $100. That's probably too much, but $100 per month. Okay, and then amount that you didn't end up using, that will be taken away every month. That will be kind of Lower Elkhorn. But then in tri-basin, you will be given $300, and you can use as much as you want during that 3-month period. Which one would you like? You will probably favor the tri-basin version. That because you can allocate that $300, across 3 months. Right? In some months, you might want to spend more than $100, but in the Lower Elkhorn case, you cannot use more than $100 per month. Okay, so that's what this temporal flexibility the benefit of temporal flexibility in quota. And then you have this carryover system where the amount that you didn't end up using can get carried over to the next period. So let's say you end up using only $250 out of $300, then you can carry that $50 over to the next period. So you will be starting from $350 for the next 3 months. That's the carryover. Okay, but there's a penalty for going over the limit. So let's say you ended up using $350. Then now you get penalty for going over that limit. So let's say tri-basin, the penalty, the amount that you used, or the excess amount that you use, gets multiplied by 2, and then that amount is subtracted from your next period's allocation. So let's say, so you used 350, so 50 is the deficit that you have. That gets multiplied by 2, so $100 is going to be subtracted from $300. Then you start with $200. Does that make sense? Okay, so that's the, but we are talking about water. Okay, not money. All right. Okay. So research question: what are the economic and hydrologic impacts of the quota design? Okay, and also how should we design quota? Okay, and I will do. I did some numerical simulation analysis of various quota designs. Okay, calibrated to corn production in Southwest Nebraska. Okay. So here's the summary of the results. So profitability and irrigation amount is highly sensitive to quota design. You know, how you design quota system is very important. It has very big impact on the farming profitability and also irrigation amount. And allowing full carryover of quota is economically very efficient the most. And finally, initial quota endowment, in addition to base quota, can dramatically reduce the economic cost of quota. Okay, so here's the method. I'm not going to talk about this very carefully, but for given quota design, okay, agriculture producers assume to maximize profit over the 50-year period. Okay, and when producers make decisions, they need to consider how, the impact of the amount of water you use currently to the future periods. If you use too much water, then you will be punished, right? And then you will be affecting, your current decision is going to affect your future decisions, okay? All right, and in this simulation, the calibrated model suggests that the farmers use 12 inches on average, okay, annually, and that's consistent with the historical water use in the Southwest Nebraska, okay? All right, so there's a lot to unpack here. So this is the result with the annual quota of being 10 inches. So you're trying to achieve 2 inches water use reduction. Okay, 12 inches is the amount that farmers would use if there is absolutely no regulations. Okay, and you're trying to achieve 2 inches water use reduction here. That where annual quota is 10 inches. Okay. And we look at 3 outcomes: profit, irrigation, and banked quota. Okay, and across columns we have different allocation period length: 1 year, 2 years, and 5 years. Okay, and on the x-axis we have year. So we are looking at the time path of profit, irrigation, and banked quota since the start of the quota. Okay, and we have with the results, outcomes are color differentiated by the maximum carryover ratio. Basically, with maximum carryover ratio of 0, you are not allowed to carry over at all. Okay, but as the number increases, you can carry over more of your quota to the next period. Okay, so let's look at the red line at the bottom of all the panels. So So if you look at the left upper corner, if you are not allowed to carry over, you would make $110 per acre, okay? But if you expand the allocation period length from 1 year to 3 year, so you're allowing a lot more flexibility, to allocate a quota across years, then your profit shoot up to about 160. And that's how powerful it is to have temporal flexibility in your quota system, okay? And now let's look at what carryover does. And again, we're gonna compare the red line at the bottom line of each panel and the green line where maximum carryover ratio of 1, which means that you are allowed to carry over up to 10 inches to the next period in a 1-year allocation, okay? Okay, so what happened, as you can see, profit goes up from 110 to 175. And also that shows also how powerful it is to allow some level of carryover for farmers. Okay, if allocation period length is 1 year, okay, that's very economically powerful for farmers. Okay, and how they are achieving it? Well, so if you look at the irrigation rows, you can see that if you look at the green line, you can see they start from lower amount of water use than the quota, right? Quota is 10, annual quota is 10, but they started off with 7 inches and it gradually increases water use. But then when they're doing that, they're building water bank. They're building the quota that they can use in the future, right? Yeah, I mean, that's basically what we do too, right? We have savings so that some big events happen. Some people get sick and you want to pay for the medical costs. Okay, that's exactly what's happening here. You're preparing for the very, very dry year like 2012. You are preparing, you're building a quota bank to prepare for those dry years. Okay, and then yeah, so under maximum carryover ratio 1, farmers ended up using 9 inches, okay, instead of 7 inches under 1 year, without carryover, okay. So there's a dramatic difference in amount of water used and also profit depending on how you are designing quota, okay. Oh, okay. Also, one thing you can notice here is that when the maximum carryover ratio is 3, that means there's absolutely no limit. At least in this case, there's no limit on how much you can carry over to the next period. Then water use eventually end up at the right about the annual quota, 10 inches. So that means as long as you're allowing farmers to carry over as much as they want, they can kind of expect the annual quota being the actual water use. So there's a lot more predictability for the administrator of this to know what's going to happen in terms of water use. But if carryover is limited, you don't water use is going to be less than the annual quota, and you kind of don't know how much less water use than the annual quota you would have from farmers. Okay. All right. So this is the this plots. So each dot represents a single quota design. Okay, and on the left hand side, on the y-axis you have average annual profit, and on x-axis you have average annual irrigation. So this one. So let's look at the imaginary vertical line at the 9 inches. Okay, so if you do that, there are multiple quota designs that would achieve 9 inches of water use. That means 3 inches of reduction. Okay, but what the dots that are at the top is the most economically efficient one, because you are achieving the same amount of water use reduction, but at the higher profit, right? So, and you can see that the top, like frontier, right, is dominated by designs that has full carryover. Okay, so full quota designs that allow full carryover are more economically efficient than the the designs without full carryover. Okay. All right. So we saw here that farmers start slow, get to build water bank at the very beginning, right here. Right. Okay. But we can help farmers by giving quota on top, quota endowment on top of the base quota, which they would get anyway. For example, if you go back here, farmers in Tri-Basin get 27 inches every year. But why don't we start at the very beginning? We can give extra to 27 inches. And that could actually help farmers a lot, especially at the early period. Okay, so here, if you give 15 inches of quota on top of 10 inches, okay, then that is the purple line. Farmers immediately starting lots of water. Well, not lots of water, but they're close to the annual quota, right? So they don't have this period of trying to build water bank, and that helps farmers a lot. Okay, and this amounts to $300 per acre over the 20-year period. So that has even though it's only 15 inches, that is given at the very beginning, okay, it has a very powerful, it's very powerful for farmers. Okay. All right, so conclusion. This is, I'm kind of repeating myself here, but economic and hydrologic outcomes are highly sensitive to quota design, okay? And full carryover offers clear benefits, more economically efficient, resulting in higher profitability for farmers, okay, compared to designs without full carryover. And also keeps full carryover keeps actual water use closely aligned with the annual quota, okay? And finally, providing an initial quota endowment in addition to the base quota at the very beginning can substantially reduce the economic stress during the early years of implementation. Okay. All right, thank you.